My talk has to do with combinatorial applications of basically Clifford algebras, but essentially really particular subalgebras of Clifford algebras. And so I'll get into maybe the details of what those are, but basically I only care about, well, I care about several Clifford algebras, but I can construct three particular algebras that are of use in combinatorial applications within a number of Clifford algebras of appropriate signature, and only the signature really matters. Zeons, from the title, are actually going to be generated. The Zeon algebra is generated by generators that commute n squared to 0. And so actually those could be constructed as a subalgebra of a Clifford algebra of balanced signature. So something like CL2n2n 0 would work, because in CLNN I can construct basically an isomorphic copy of the Grassmann algebra. So things would anti-commute n squared to 0. I just need disjoint, pairwise disjoint generators. I group two Grassmann elements together at a time, and as long as they're disjoint, they commute past each other. The easiest way would probably be, if I'm looking at CLPQR, just consider CL002R or 2n, and then I can get n generators that commute n squared to 0, and that's kind of the starting point for my talk. Of course, CL010, everybody knows complex numbers, but we can do reflections and rotations. So all the geometry has been sort of known for some time. And of course, these days, quaternions are quite important in computer applications, and I guess a lot of video gaming applications. But what I started seeing whenever I was playing around, first learning about Clifford algebras, was just considering, generators and blades and orthogonal vectors. That really, whenever I started looking at hyperplane reflections and arrangements of hyperplanes or groups of hyperplanes and subspaces, they really have this combinatorial characteristic. And basically, if you look at the Cayley graph of hypercubes, and by hypercubes, I'm meaning all the subspaces of an n-dimensional space, they start looking something like this, where basically you have a cube of subspaces. And this looks a lot, and so this is just the Cayley graph, but it looks a lot like a hypercube that you would see in computer science, where these things are, each vertex is basically a bit string of length 3, and starting from 0, 0, 0 and going out to 1, 1, 1. And at each step, two vertices of this cube are adjacent if the difference in their Hamming weight as bit strings is 1. And what it means is their dimension as subspaces differ by 1. And throwing away the anti-commutativity and going with a commutative picture, this basically is just basically it's a hypercube, and basically, you can do things like consider problems in combinatorics and coding theory, which I'll get to a little bit later, and I'll be talking about that in particular next time. That's been a rather recent development of actually talking about that. But so the multi-index notation has a natural binary representation. So I'm taking the product of some number of generators, and I'll just index it by a subset. Instead of writing the product over the particular generators, I'll just put it as a subscript, a subset of which generators appear in the product. But then, of course, subsets are in one-to-one correspondence with binary strings, which are in one-to-one correspondence with integers, because you can do the integer representation of a subset. And here, whenever I do a multiplication, this is not for Zeons, but in general, in the Clifford algebra, if I have multi-indices, EIEJ is plus or minus EI set symmetric difference with J, which represents really an exclusive OR if you're looking at it in terms of bit strings, which is how I can move around in this graph. And actually, I did a paper a long time ago about random walks on hypercubes using particular Clifford subalgebras by just using the multiplication to derive the log. But the Zeon algebra came up because I was interested in finding paths and cycles in graphs, and that's an NP-complete problem. Even determining if a graph has a Hamiltonian cycle, a walk that goes all around the graph, visiting every vertex exactly once, returning back where it stops, that's NP-complete. And I started looking at ways of representing graphs using elements of Clifford algebras or Clifford subalgebras. And the most efficient way to do that, it seems, is to have the Zeon algebra. So it's generated by zeta 1 through zeta n. That's what I would typically use for an n-vertex graph. The commutation relations, so it's commutative. They commute with each other and they all square to 0. And I can extend my multi-index notation to the Zeons. And I can think of them as just disjoint Grassmann bivectors. So just pair off Grassmann generators. I just need twice as many of them to form the Zeon algebra. But this will be an algebra of dimension 2 to the n, just like the Clifford Algebras CL n0 would be. But the power is I can do a lot of stuff with combinatorial problems. And the real power, I'll show you a little bit later in my talk. But so these are commutative analogs of fermion algebras and subalgebras of Clifford algebras, of course. And Clifford algebras provide the, probably not underlying framework, maybe the overarching framework, but for everything here. And so it's very simple. If I just multiply some of these things out, basically anytime you see a square, it goes away. And so you have this sort of collapsing of terms. And that actually is nice because I can do things like pruning trees in algorithms inherently by the properties of the algebra. So I don't have to write an algorithm to do everything that people usually have to do in order to solve path problems and graphs, because a lot of the work is done by the algebra itself. So this is what I mean by my multi-index. Zeta sub j is the product over all little j and j of the generators. And the generators can be any orthonormal basis for a vector space, and then I'll just define the multiplication so that the squares are 0. So a general element, I mean, it's a sum over this this basis set of indices. That's the power set. 2 to the n represents the power set of the n set. So subsets are the subsets are the multi-indices. Some notation, the scalar part, I'm also sort of using this grade projection notation. So the scalar part, here it's real. The first ones that I did were always real. Since then, I've done some work with Zeons with complex coefficients. But there's a real part and a dual part. The reason for the word dual is because you can think of these as higher dimensional dual numbers. So it's sort of an algebra of dual numbers. And you can think of some quantum structures related to this. But mostly I want to talk today about just enumeration problems in graphs. We've done some stuff with routing problems, with communication networks, and some things with colored graphs. We're not just finding paths through graphs, but finding paths, heterochromatic or homochromatic paths in colored graphs. And graph colorings can come in various flavors as well. You can color the vertices or you can color the edges. So we're going to, the idea is consider adjacency matrices of graphs, but build adjacency matrices whose entries are actually elements or generators of one of these algebras. And by doing that, you associate algebraic structures with graphs and then just use the algebra itself to sieve out the desired structures. So adjacency matrix, if I have a graph with 5 vertices, the adjacency matrix would be a 5 by 5 matrix of zeros and ones. And the entry in row I, column J is 1 if vertex I is adjacent to vertex J in the graph. It's 0 if otherwise. And it's well known that if you take powers of that thing, you count you actually get the total number of walks of whatever the power is, that many steps from one vertex to another. But you get all walks. So you could have walks that just bounce back and forth between the same pair of vertices 50 times before moving on. And so you can't tell, you don't want to count walks that necessarily revisit vertices a lot of times. You want to know how many ways you can get from point A to point B without repeating yourself, repeating a step. So the adjacency matrix doesn't let you do that, but you can construct an adjacency matrix whose entries are these Zeon generators, and then anything that revisits a vertex is filtered out. So the definition of this, I'm just going to replace the ones in the adjacency matrix with generators representing a vertex, the next vertex that I'm going to. And the complexity is interesting because the computational complexity really just depends on the complexity of the graph. It depends on how many paths there are. So it depends on the structure of the graph very much. And there's an algorithm that I'm going to give an example of in a little bit that actually, if a graph is fairly dense, meaning there are lots of edges in the graph and lots of connections between vertices, the algorithm is actually faster. So the more dense the graph is, the faster the algorithm works. And it depends just on the structure of the graph, not on necessarily the number of vertices, or it depends mostly on the density of the graph. So this is a simple result from a long time ago now, I guess. It was published in 2008, but it was from 2004, I think, 2005. I presented a paper in Toulouse, but if you construct this matrix, which I'm going to give an example of in a minute, you take the kth power of the matrix and you look at the trace, you get actually all the cycles of length k in the graph, which isn't the most efficient way to find cycles or paths in graphs, because this actually computes all of them all at the same time. But there are much faster ways of implementing an algorithm like this. Paths and trails are counted in the off-diagonal elements. So cycles appear on the trace along the main diagonal. Paths and trails show up in off-diagonal elements. So here's sort of a nice theorem. If I want to know how many walks there are in a graph on n vertices of length k, so walks of length k from the ith vertex of the graph to the jth vertex. And this notation just means really look at row I of this matrix. So this matrix a to the k, multiply it by zeta I, so that accounts for the initial step of the walk, the vertex that I start from, and look in the jth column. And what I get is a sum, a linear combination of zetas from the Zeon algebra, whose coefficient actually tells me the number of paths of length k from the ith vertex to the jth vertex on vertices indexed by I. So it doesn't tell me the actual path, but it tells me the vertices involved, and then I can recover the path pretty quickly. So just by considering, if I calculate the kth power of the matrix, which actually is not terribly efficient, but I could just look in row I, column J. However, if I just prepare this vector, zeta I, with the ith row pre-multiplied by zeta I, and then look at the jth entry of that for k equals 1, I'll know if there's a one step, if I and j are adjacent. And if they're not, I could just then multiply by a again, and then this would be a squared, and I could check that. And the complexity is lowered by at least n squared maybe, right? So just multiply by the matrix every time until you find a path, and then you could find all the so-called hop minimal paths from one vertex to another. So here's like a picture of what I'm talking about doing. So here's a simple graph. So just a collection of vertices, got some edges, and then here's the nilpotent adjacency matrix for that. So it's 10 by 10. I've put nilpotent generator zetas, which again are just, you could think of disjoint Grassmann pairs. And if I take the 10th power of the matrix and compute its trace, I get 80 times this full index set, right? So actually, because each one appears with two orientations at each spot along the diagonal, because the cycles from 1 to 1 would be here, and 2 to 2 would be there, and 3 to 3 would be there. So they're overcounted by a factor of 20. So there are 4 Hamiltonian cycles, which are like the traveling salesman problem. It's paths that leave a vertex, go all the way through every vertex exactly once, and return back where they started. But again, that takes a little work to do that. But here's an algorithm. This is what I was saying I consider sort of the real strength of the approach. This is the algorithm to enumerate all the shortest paths from one vertex to another. So I have my adjacency matrix C. I have an initial vertex where I'm starting and a terminal vertex where I'm hoping to go, and I want to find all the hop minimal paths, like all the shortest paths from V0 to V infinity in the graph. I prepare my initial row vector, and as long as I haven't gotten to my destination and I haven't like exhausted all possibilities, which eventually happens, I just multiply by C. And then as soon as I either reach my destination or everything gets annihilated, I return the result. So that's what this actually does. Prepend the starting vertex so that, if I revisit my starting point, that goes away, and then recover all one-step paths starting from V0 and just keep going until I either find the terminal vertex, find my way there. But the thing is, once I find my way there, if I find my way there, I not only have a path, I have all the paths of that length, that minimal length from V0 to V infinity. And it's actually a pretty quick algorithm. So that's one part of the power of this. It gives me all the minimal paths. Not only that, as it turns out, if I had different problems, I want to count heterochromatic walks in a colored graph or heterochromatic edge labeled trails in an edge colored graph, or several other types of problems on graphs that have to do with enumerating ways of getting from one place to another. It's the same algorithm. All I do is change the definition of C to a different definition to cover the kind of structure that I'm looking for. I can even generalize it so that maybe I want to keep track of weights of edges and just annihilate any path that exceeds a certain value. So if I have maybe some constraint like time constraint or some energy constraint, I can just make those things automatically vanish once I exceed the allowed time or the allowed energy expense. Right? So for example, I did a couple of, these are all done in Mathematica. I have some Mathematica package, a couple of them, but Cliff Math is the one that I use for a lot of stuff. It does Clifford Algebra computations and Zeon and some of the other Clifford subalgebras that I use a lot. And it's really handy for doing graphs and presenting them nicely. So here I've got a 100 vertex graph, and I just generated it randomly. I don't remember, I didn't include the probability. Basically, I just generated, took 100 vertices, made each pair adjacent with a certain probability. And then I just randomly selected 2 vertices. So V40 is the initial, V61 is terminal. So I'm looking for all the paths from the green one, all shortest paths from the green one to the red one in here in this picture. And there turns out there were 2 of them. And this is a pretty sparse graph. So it actually took a little bit longer than you might expect, but it took half a second, which is still pretty decent for a 100 vertex graph. And to recover all, this is 5 steps from V40 to V61, and they occur on these vertices in the graph, this one and this one. And those are the only 5-step graphs from V40 to V61 in this graph. So I moved up to a 300 vertex graph, and I kept it sparse just to keep it interesting. So I lowered the probability. But if this were more complicated, it would actually be quicker, and I'd probably have fewer, maybe I'd only have one or two, or maybe only one. But anyway, there are only two paths here. Looks like 6 hops. 6 steps to get from 243 to 35. So from the green one to the red one here, it took me 1.3 seconds to calculate that. But again, if it were more dense, there would be fewer steps. There would be fewer steps of the algorithm. The algorithm took a few steps to get there. And then I did another example with a 500 vertex graph, and the green one's here. You can barely see it, and the red one is there. But there was only one, and it's actually 4 steps. Took a couple of seconds to find that one, but that's the only one in the graph, and that's the unique shortest path. There could be others of greater length, but the shortest path between 294 and 10 is 4 steps, and those are the vertices involved. And then I went ahead and just decided to do 1,000. Oh, there's the green one. So there's the initial vertex, number 710. 480 is in there somewhere, but once it gets this big, it's actually a pretty sparse graph, even though it doesn't really look like it, just because there are 1,000 vertices. And it took 9.5 seconds, but as it turns out, the shortest path from 710 to 480 requires 4 steps, and there are 7 of them in this graph. Oops. Yeah, there's 7 of them in that graph, and they're all enumerated right there. So, and there are actually other speedups for this as well, because the algebra is commutative. This is all done with Cliff Math, which has its own multiplication operator defined. But with the Zeon Algebra and a couple of other, there's an item Clifford algebra that I use sometimes, where the generators commute and square to themselves. And there's a sim Clifford algebra where generators commute and square to 1 or -1 or 0, well, not 0, but 1 or -1 or whatever you want. And those are commutative, so you could actually get a nice speed up by just overloading the times operator in Mathematica to get quicker, generate some quick examples. Okay, so this is an example of what I was talking about, the vertex colored graph. Suppose I wanted to count all the walks from one vertex to another without repeating a color of a vertex. Or all the walks from one vertex to another in this graph where I don't repeat a color of an edge. Or if I want to keep the colors of, I want it to be all on one color edge or all on one color, visiting only a monochromatic path here where all the vertices that I visit are the same color, I can do that as well with just some tweaks to the algebras and maybe defining a slightly different algebra. But again, you're given a colored graph, an initial vertex and a terminal vertex, and I want to find all the shortest monochromatic or heterochromatic paths, from V0 to V infinity. It's NP complete. You have to deal with combinatorial explosion. Most algorithms use some sort of heuristics and pruning of trees to explore the solution space, but the algebra does all the work for you here with that. And here's, I define a new adjacency matrix, nilpotent adjacency matrix, using colors instead of vertex numbers. And then the algorithm looks the same as the previous algorithm, and I just look at the ith row and jth column to find the paths, heterochromatic paths from vertex I to vertex j in the graph. Then if I want to move on from static case where I just have one graph and I want to have a dynamic situation, I've got things moving in space and maybe they're forming connections based on proximity or something, like with with cell phone towers connecting to phones or mobile communication networks, satellites. What I can do is just kind of discretize the process. I can figure out when the topology of the graph changes and take a snapshot, and then I have a finite, or maybe not finite, but I have a sequence of graphs, and I can construct a sequence of associated adjacency operators to go with those. And then I just consider powers of those until I find the paths that I want. So if I want to consider, I have some vertex. This is sort of a mock-up of what might happen if I've got the little circled ones are sort of supposed to represent satellites, and then the dots without circles are stations on the ground, and the circles are moving. And so as they get within, visual range of a dot on the ground, they automatically connect to it, and they can store and carry information from one dot to another and relay it that way. And so if those are moving, I can take this snapshot and construct an adjacency operator, wait till the topology changes, take another snapshot, form a sequence of matrices, and then, I can find all the paths by just considering, this is my initial vertex V0. Maybe I have 3 steps in the first frame if I'm looking for 3-step paths, or maybe I take 2 steps in the first frame, but then the topology changes, so there's 1 extra step in the second frame. And so the C's indexed by 1, 2, and 3, these are adjacency operators, nilpotent operators, representing graphs with different topologies. So here I could take 1 step with the first topology. The topology changes, I take the second step from wherever I left off in the first one. And in the third step, I take it in the third topology. So these are all those sorts of possibilities for taking 3 steps. And so to obtain all k-step paths from V0 to V infinity, in the first m or fewer frames, I consider all the ways that I could take steps in those m frames, m different graph topologies from V0 to V infinity. The thing is, in addition to letting the algebra do the work in solving these problems, we have extra algebraic tools for establishing other results, theoretical results, like limit theorems or existence theorems. So I spend a lot of my time either setting up, I've done a few applications like this, but then I also spend time working on limit theorems and existence theorems and doing some of the theoretical work. And even, we have all these sequences of Zeons who want limit theorems, and we have to discuss convergence. So I have, some analytical work on establishing some of these theorems and limit theorems. And of course, just doing calculus with the Zeons. So defining elementary functions and considering inequalities and norms. And then polynomials come up and calculus comes up, and of course, symbolic computations to go along with all of those things. So I think there's enough of a body of machinery now to maybe start going back and looking at some of the more theoretical aspects of maybe some theoretical aspects of graph problems. And more recently, so aside from that, there are other extensions. So there were lots of generalizations to do with graphs. I mean, you have graphs, standard ordinary graphs. You have the dynamic case. You have colored graphs, vertex colored, edge colored. Dynamic cases for all those. This is a picture of a hypergraph. So in ordinary graphs, you have a collection of vertices, and each pair may or may not be adjacent to each other. So they could be an edge like this. In a standard graph, you just have something like vertex 4, vertex 6, they're adjacent or they're not. In a hypergraph, an edge is really just a two subset of the set of vertices. In a hypergraph, those subsets can be bigger. So this subset of vertices, all 3 of these is an edge in this hypergraph, and these 3 are an edge in this hypergraph. And so these 3 vertices form an edge. And that's a generalization that has lots of other applications in computer science. It's related to Boolean satisfiability. We've also done some work with that. These have started getting attention with applications in cancer research, even game theory, just lots of places. And I think they've been around for a while, but I don't think they're very difficult to work with by hand. So having technology and actually being in an age when we can code some things and see what happens makes it a little more accessible. But so we've done a little work, and this has recently been accepted for publication. It hasn't actually appeared yet, but Zeon and Eigenvalues formulations of hypergraph problems, where a lot of that stuff on problems with graphs has now been, those results have been generalized to hypergraphs, including random walks on hypergraphs. You can count paths on hypergraphs, counting paths and cycles in hypergraphs, and rephrasing or reformulating some open problems on hypergraphs in terms of the algebra. Because once you have some algebraic tools, you might actually have a chance at solving some things that have been open for a while. So this might look familiar because the structure of the theorem is very similar, except now I got two different kinds of generators. I've got the ones that square to zero and the ones that square to themselves, but I'm able to enumerate paths in hypergraphs using the same kind of thing. Define a nilpotent adjacency operator that represents the hypergraph, and we can formulate algorithms or hop minimal path algorithms for the hypergraph, just like and it would have the same structure except for maybe the algebraic elements being slightly different. Instead of just zetas, I've also got epsilons, but the structure of the theorem is essentially the same, and the structure of the algorithm is still essentially the same as the previous one. I recently did some work with the Zeon combinatorial Laplacian. The classical Laplacian, for a graph, you have a degree matrix. It's just a diagonal matrix. Along the diagonal, you have the degrees of the vertices, which are how many neighbors each one has. Go ahead. How much time do I have?
Stacey, you have about 5 more minutes.
Oh, okay. That's no problem. I'm almost done.
Awesome.
Thanks. Yeah, so that minus the usual adjacency matrix gives you the combinatorial Laplacian. And that graph has the property that any miner will enumerate the spanning trees of the graph. So a subgraph that is a tree, so it has no cycles, but it covers every vertex of the graph. So a little bit different case happens with, I've defined a Zeon version of that. And as it turns out, as long as you don't have any isolated vertices, like degree 0 vertices, the Laplacian is actually invertible. The inverse exists. And the inverse reveals numbers of paths between vertices in the graph. It does all of them in the inverse. That was published, I don't know, I think I was talking about that one in 2020 at the last ICACGA meeting. But anyway, I'm working on the Zeon spectral theorem is done. It's under review right now. It's already been through one round of review. So there's a spectral theorem that goes along with that. And the most recent thing, I just wanted to give a little preview because tomorrow is a talk I'm giving based on some joint work with another one of my students on coding theory. So an application of Zeons in coding theory, and also this other algebra that I mentioned, the Clifford algebra, where everything's commutes, the generators commute in square root of 1. So yeah, this was the thing with the combinatorial Laplacian. This is what the theorem says. It looks very much like the null structure theorem that was there before, but now this is the Zeon combinatorial Laplacian, which is very close. It looks a lot like the classical Laplacian. But if you look at the inverse, as long as you don't have any isolated vertices, you don't want any of those. But then as long as there are no isolated vertices, like a vertex by itself with no neighbors, this thing is invertible, lambda is invertible. And when you expand the inverse and look in row I, column J, you can count the number of paths, all the paths from I to J. Eigenvalues. So again, this wasn't really so possible until some work was done with Zeon polynomials. So that was more of the pure work, finding zeros of Zeon polynomials. Now you can define the characteristic polynomial of a matrix with Zeon entries and form that thing and look for zeros. And those things tell you some, well, I haven't done that yet, but it looks like the eigenvalues of the combinatorial Laplacian will also tell you something about the paths of the graph, but I don't have the specifics of exactly what that formulation looks like as far as what the coefficients actually represent yet. And this is the last thing, the most recent thing for tomorrow's talk, the Clifford algebra. I can just take disjoint pairs in CLNN, pair them up. This was actually the first Clifford subalgebra I defined back in 2003 or 4, whenever I was doing my dissertation. And I was applying this to some graph theory problems back then, but it makes sense. This is the one in which multiplication is really just like doing an exclusive OR of bit strings. And the exclusive OR is equivalent to the set symmetric difference of subsets. And I can generate binary linear codes this way. And we can combine properties of the Clifford and the Zeon algebra for some nice calculations, generating codes and verifying codes, and correcting errors. We can say something about the error correction capabilities of a code in terms of algebraic properties of the generators. And so we can form an element and generate an entire code from it by just considering products of elements or powers of elements, powers of generators, which you wouldn't probably do in practicality for coding theory, because ones and zeros are pretty efficient. But we have some new tools for establishing things like limit theorems and existence theorems. But that's something that I'll be talking about tomorrow. And thanks for your attention. If you're interested in any of this stuff, I've got a lot of links to stuff on my webpage. Thanks.